So, Brian, we have two puzzles here, really. One is how you get a white dwarf to explode in the first place. How do you actually add enough mass to it to make it go bang? But then secondly, it should be, the remains should all be made of nickel-56, but we're finding all these other elements. What's going on there?
Well, I think the secret is going to have to be looking and getting the white dwarf so that it's no longer degenerate at the time of the explosion. Because the whole thing's degenerate at the time of the explosion, the whole thing's going to turn into nickel-56. So we need to do something to it. And the best way to get rid of degeneracy is to somehow dump a bunch of heat into it, or stir it up, or do something that makes it not be that nice little quiescent ball of gas.
Yes, you don't want a perfectly symmetrical, nice spherical thing that's just resting there and then you drop the last little feather on the top and it all goes bang. We want it to be seriously traumatized even before the explosion goes off.
Yeah, so it turns out, a number of ideas of how we might do this. So maybe the most easily thought of is you just take two white dwarfs, and instead of doing anything nice, you let gravitational radiation leave the system, brings them closer and closer, and then at some point what happens is they merge, and when they merge it makes a real mess.
That's not pretty.
And so that mess, that does not look like a nice degenerate ball of electrons.
It's precisely degenerate pieces where the density's gone too high within it. Some sort of mix of degenerate bits and not degenerate bits and some really complicated spirally pattern.
Right, and so if you can ignite that, if that ignites, and there's a big question of whether or not it will in all cases, then you would get a ball of stuff that's going to be a bit messy, but probably is not going to be all nickel-56. So that's one idea.
Okay.
And you can also see this is a good way to make a Type 1a supernova. It's happening because these white dwarfs that will be made, by two binary stars sometimes, come together because of gravitational radiation. So it gives you essentially, how often it happens. Not very often, but it can sort of explain what we see. Now, so that's one idea. Another idea is in many respects the most popular, but it's a little more complicated. And essentially it says that if you have a white dwarf, they start to simmer first before they reach that magical point of
so you're just gently dumping matter on the surface in this scenario, are you?
Right, and so...
But before it doesn't sort of suddenly go bang at one point, it starts simmering.
That's right, and the reason is that imagine you have a white dwarf which is approaching the Chandrasekhar mass. At that point, every piece of material you put on, the whole thing gets a little smaller. Now, they're not all the same density. They actually have a density gradient such that the core is denser than the outside.
Yeah, it would have to be to support the
Absolutely,
mass, yeah.
That's right. And at some point, before you reach the magical 1.4 solar masses, you get to that density and temperature where carbon wants to start burning into oxygen.
Mm-hmm.
And so that will simmer. And when you simmer, then that's going to start liberating heat. The heat will bubble up, it turns out, in some cases. It will lift that degeneracy in the center. And so that will eventually, we think, run away in this simulation. What happens is that the simmering starts. It starts happening faster and faster and faster until it runs away, and then suddenly it creates a detonation right there. And part of the star is already growing, so it doesn't completely burn to iron, it burns to oxygen and sulfur. And the inner bit, which has sort of been cooked more, that tends to give you the iron.
So it's kind of a slow start explosion. How long are we talking about for the simmering?
This is all less, so the simmering is probably on order of decades to centuries, but then it's an exponential process. So it's one of those things that each bit happens, and then when it runs away in a period of about a second. So 1,000 years maybe in the making, and then boom, when it does run away, it happens in that last exponential half-life is the one that rips the star apart.
But because it's been simmering for so long that a lot of the stuff is too far out and the degeneracy's already been lifted, so it doesn't all turn to nickel-56.
That's right. And then finally, a popular one recently is, we think sometimes if you have two white dwarfs, one of them will be made of helium and be able to dump helium onto its partner. And helium, when it settles onto a white dwarf, can detonate itself on the surface of the white dwarf. And that's what you've just seen here, is you've seen material coming on from a white
Helium's
dwarf.
being dumped, and then
Yeah.
you get a helium flash or
You
something.
get a big helium flash. Now that helium flash is going to send pressure wave into the center of the star. And we think that sometimes, actually quite frequently, that pressure wave will again essentially compress the center of the white dwarf to a pressure and temperature such that carbon will detonate. And when that detonation, because it's almost degenerate, the whole thing will start to burn again because the thing has been disrupted, degeneracy has been lifted, the thing started expanding from the detonation, and again you'll turn the center into nickel 56 and the outer bits into lighter things. So those are three ideas. The question is, we don't know which one is right, and that's a bit of a problem. And so you might think it's hopeless, but remember that type 1a supernovae, we can actually see them because they've occurred in the last millennia in our own galaxy, the Milky Way. So if we go out and look at them, here is the three easy-to-see remnants. This is SN 1006, seen by the Chinese. This is Tycho's supernova, seen by Tycho Brahe. And finally, Kepler's supernova remnant, seen by Kepler and Galileo. And so if you look in the center here, you can see that's just a nice spherical blob. There's no sign of really any mess or anything.
Yeah, I mean, you think if you were merging stars together, you'd have some horrible pattern that would blast off in some directions and not others. This looks like,
It's nice and neat.
symmetrical, yeah.
This one's surprisingly nice and neat, too.
That one maybe a bit
That
more
one's
swirly.
a little more interesting. It turns out this one seems to have a band of like nitrogen and stuff that you might think came from another star, but two look kind of nice and one's a little messy.
So which models do you think this would argue for?
Well, it seems the Simmering model seems to fit this pretty well, but there's a problem. And that problem is that if you go through and you look at, for example, the center of the Tycho remnant, and you look at all the stars, we want to look for the star that was donating the material.
Yeah, presumably either the Simmering model or the Helium model, you've got another star there which is dumping the gas on the surface to make this happen. And that other star won't be destroyed in the supernova explosion. You can destroy planets in a supernova explosion, but stars are just a bit too massive to be destroyed in that stuff. So
That's right.
Where is the star?
Well, so it turns out that when you go through and look at all the stars, you don't really see anything. What you expect to see is the following. Imagine you have a star donating material to the white dwarf. Well, they're rotating against, they're orbiting each other. And when that star explodes, well, the other star is going to go off at the orbital speed, rotating at the orbital speed, and that turns out to be several hundred kilometers per second. Should be easy to see, and yet we don't seem to ever see it.
And you spent a lot of time looking.
And we have spent a lot of time looking, and much to my dismay, we haven't seen it. And there's another similar problem, is that that star, when the explosion goes through that star, it's going to mess that star up. And when you heat a star up, it gets bright. And if we look, for example, at one of the nearest one of these exploding stars in 50 years, you don't see anything. Indeed, if you go through and you model what you expect to see when you blow something through a star, it makes things bright, almost as bright as the supernova itself.
So the supernova is still rising in brightness while the radioactive elements start decaying.
Yep.
But for the very first days, you get a much greater brightness because of this hot, traumatized companion star.
That's right. And so this is what you would expect to see from that companion. And of course, when we do look at it, we don't see anything at all. We see no sign of that. So we are missing sort of the smoking gun for the donor star. And so, this leads us to, I guess, a number of possibilities and a bit of clues that we should sift through and think about.